In this task, we are being asked to determine the conversion of the species A of a CSTR and PFR reactors connected in series. The task gives us following information. A reacts with a rate constant K to P. Here we have a second order reaction. The task specifies that the reaction rate of species A is going to be equal to negative K times Ca elevated 2. The task also gives us the rate constant K, the volume of the CSTR, the volume of the PFR, the volumetric flow rate, the concentration Ca0, which is at the inlet of the CSTR. So the conversion of the whole process is going to be equal to the entering molar flow rate of the species A, Fa0, minus the leaving molar flow rate of our system, which is Fa2 at the end of the PFR, divided the entering molar flow rate, which is Fa0. And we know that the molar flow rate is going to be equal to the volumetric flow rate times the concentration. So for Fa0, it's going to be volumetric flow rate times the concentration A0, which is at the inlet, minus the volumetric flow rate of the concentration at the outlet, which is Ca2, divided the volumetric flow rate times Ca0. So we can factor out the volumetric flow rate. So volumetric flow rate times in parentheses Ca0 minus Ca2 divided the volumetric flow rate times Ca0. So the volumetric flow rate cancels out, and this will be equal to Ca0 minus Ca2 divided Ca0. So Ca2 is unknown, and we need to write Ca2 as a function of the given information, which is on the upper right side of your screen. So our first step will consist in doing a species balance of a species A at our PFR. So let's sketch our PFR here. So on the left side, we have the molar flow rate Fa1, which is coming from our CSTR, and this is equal to the volumetric flow rate times the concentration A1, which leaves our CSTR, and leaving our PFR. We have the molar flow rate A2, which is equal to the volumetric flow rate times the concentration Ca0. So for a plug flow reactor, we have a given length L. Here we have our cross-section area A. And for a species balance of a PFR, our approach consists in cutting a segment. And here we have the segment with more details. So this segment has a thickness of dc. Here we have dc. We have our cross-section area A here. And the volume dV is going to be equal to the cross-section area times dc. And within this segment, we are also having the reaction Ra taking place. And on the left side of our segment, we have a molar flow rate, which is Fa at position Z. So this would be the C coordinate here with position C, and here we would have position C plus dc. And leaving our segment, we have a molar flow rate of the species A at position C plus dc. So our species balance, the change of the species A with respect to time, will be equal to the intermolar flow rate, which is Fa at position C, minus the leaving flow rate, which is Fa at position C plus dc, plus the reaction rate of the species A times the volume of the segment dV, so as a quick reminder for this term, we use Taylor to expand this term. So Fa at position C plus dc is equal to Fa at position C plus the change of Fa at position C with respect to C times dc. And the change of the species A with respect to time is going to be equal 0 because we have steady state. So 0 is going to be equal to Faz minus, and we insert a Taylor expansion, Faz plus the change of Fac with respect to C times dc plus the reaction rate of the species A. And instead of writing dV, we are going to use this expression, so A times dc. So this would be dV. So these two cancel out, and we would have 0 being equal. So negative and positive is negative, so negative change of Faz with respect to C times dc plus Ra times A times dc. We will divide this with dc. So these two terms are equal to 1 now. And in the next step, we will sum our equation with the change of Fac with respect to C to bring this term on the left side of our equation. So dFac change with respect to C is equal to the reaction rate of the species A times A and with the change of Fac with respect to C being equal to the change of the volumetric flow rate times the concentration of the species A at position C to C. If we would have a function which consists of a product uv, the derivative is going to be equal to u times v derived plus v times u derived. This is known as the product rule. Let's say this term is u, and this term is v, hence the change of the volumetric flow rate times Ca at position C with respect to C can be expressed as volumetric flow rate times the change of the concentration A species A at position C with respect to C. So this term would be our U, and this term would be our V derived plus CA C, which is V, and times the change of volumetric flow rate with respect to C, which is U derived. So here we applied the product rule, and because the change of V with respect to C is 0, because V is constant, we can just ignore this term. So this we can insert for the change of VAC with respect to C. So this would be our current term. This would be equal to the reaction rate of the species A times the cross-section area A. And with the reaction rate A given by the task, which was equal to negative K times the concentration of the species A and position C in this case, squared. So this we will insert in our equation. So the volumetric flow rate times the change of the concentration of the species A at position C with respect to C is going to be equal to negative the rate constant K times CAZ squared times A. So in the next step we want to separate the variables. So dCAC and dC we want to have in the different side of the equation. So for this we will multiply with dC. And we also want to bring the volumetric flow rate of to the right side of the equation. So dCAC is going to be equal to negative K divided the volumetric flow rate V times CAC squared times A times dC. And we need to bring CAC squared on the dCAC side of the equation for integration purposes. So we will divide this equation with CAC squared, which will result in dCAC divided CAC squared being equal to negative K divided the volumetric flow rate times A times dC. So in the next step, we're going to integrate our equation. So on the left side, we will integrate it from the entering concentration, our PFR, which was CA1, which was leaving our CSTR, to the CA2, which leaves the PFR. And the right side, we are to integrate it with respect to DC. And the right side, we're going to integrate it with respect to DC, and K, V, and A are not a function of C. So we can simply integrate this part, namely from the start of our PFR, which is position C equals 0, until the end of our reactor, which is at position C equal L. And as a quick reminder, so an integral from a lower to a upper boundary for 1 divided x elevated n dx, with n not being equal to 1, we can say that this is equal to the integral from xl to our upper boundary x elevated negative n times dx, and this would be equal to x elevated negative n plus 1 divided negative n plus 1. For x, we would have our upper lower boundary, and this would be equal to 1 divided negative n plus 1 times x upper limit elevated negative n plus 1 minus x lower limit elevated negative n plus 1. And for n equal 2, which would have in our case, is going to be 1 divided negative 2 plus 1 times xu elevated negative 2 plus 1 minus x lower elevated negative 2 plus 1. And this would be equal to negative x u elevated negative 1 minus xl elevated negative 1. And this would be equal negative 1 divided xu minus 1 divided x lower. In our case, the upper boundary would be CA2, our lower boundary would be CA1, and the variable x is CAC. Hence, we can transfer what we just integrated, this integration here. Hence, we can say negative in parentheses 1 divided CA2 minus 1 divided CA1 is equal to negative K divided volumetric flow rate times A, and this integral is simply the upper minus the lower limit, which is L. And this term is actually the volume of our plug flow reactor. So negative 1 divided CA2 and minus are positive, so plus 1 divided CA1 is equal negative K times the volume of our plug flow reactor divided the volumetric flow rate V. And we know both of these terms, VPFR and V, and we will just summarize it as tau PFR, which is the mean residence time. So in the next step, we will subtract our equation with 1 divided CA1, resulting in negative 1 divided CA2 being equal to negative K times the mean residence time PFR minus 1 divided CA1. We will multiply the equation with negative 1, resulting in 1 divided CA2 being equal K times tau PFR plus 1 divided CA1. We will elevate this equation with negative 1, inversing both sides of the equation. So CA2 is going to be equal to 1 divided K times tau PFR plus 1 divided CA1. So K, we know, this is given by the test. Tau PFR is the summary of volume of the PFR and the volumetric flow rate, which we both know. Hence, we also know tau PFR. However, CA1, we still don't know. So in the next step, we are going to determine CA1 with information given by the task.